Sivaraman possesses a wealth of expertise in power systems with a particular focus on renewable energy interaction, grid impact analysis for EV charging and infrastructure, and power quality analysis. As a dedicated member of various IEEE standards and task forces, including IEEE 2800.2 and IEEE P2844, Sivaraman contributes significantly to shaping industry's practices and ensuring the reliability and efficiency of our power systems. His involvement in national study committees of SIGA figure underscores his commitment to advancing power systems, technical performance, and active distribution systems. Sivaraman's expertise extends to a wide range of renewable energy technologies, including solar PV, wind power, and battery energy storage systems. His contributions as an active researcher in renewable energy, microgrids, and electrical vehicles have been instrumental in driving innovation and sustainability in our industry. With proficiency in simulation software such as ETAP, PSCED, MATLAB, and more, Sivaraman brings a hands-on approach to problem solving and analysis, ensuring the robustness of his solutions. Not only Sivaraman, a senior member of IEEE and a member of Institution of Engineers India, but he also holds the prestigious Professional Engineering certification. He has a role as an ambassador on IEEE initiatives, including smart cities and PES5P powering of the future, reflects his dedication to fostering collaborations and acknowledge exchange with the industry. Please join me in welcoming Mr. P. Sivaraman, whose expertise and leadership continue to inspire and shape the future of power systems and renewable energy. I hand over the session to Mr. P. Sivaraman.
Hi Kirtana, thanks for your brief introduction. I will share my screen. Let me know once my screen is visible to you. So once again, I am welcoming you all to the fifth session of IEEE ADSF SIGHT, the interaction program on solar energy. So in the last session, I have take you through the ground-mounted solar PV system. So the layouts and inverter blocks, the single line diagram and substations, etc. So in this presentation, it is a continuation of the previous presentation. So today I will explain the ground-mounted solar PV system in and design aspects. So it is important for the renewable engineer or design engineer who wants to continue their career in solar PV system in an in design perspective. This session is very useful for them. So continuing further, in the last session, I explained that in the photo in this slide, what you are seeing is an layout of the overall layout of the ground-mounted solar PV system. So this is a total. This is the total land area. So in this land area, we are going to construct a PV plant. So, so in between, these are all the areas where water logging can be happened, or this can be a pond, or there is some small river kind of thing. So these are all unused or not usable area. So in these locations, we are not able to mount any solar panel or any other engineering equipments in these areas. Okay, so and importantly, based on the site survey, so we have to identify how many usable area is there. So in those area only, we have to install the solar PV panel. So in this slide, there are 4 inverter rooms or inverter blocks are there. So this is the one IR1. This will be 2. This will be 3, and this will be 4. Okay, so totally 4 rooms are there. So for easy understanding, um, all the rooms are given a different color so that we can able to identify easily. So this is the location. The inverter rooms will be there. So in the inverter room, the inverter room means this is an inverter room. This is an inverter room. So in this inverter room, that there will be an room. Some locations inverters will be placed indoor, and some location inverter will be placed outdoor. Then there will be an transformer, inverter duty transformer. This is an inverter duty transformer, and switch gear, medium voltage switch gear. So these are all the equipments will be placed in this inverter room. So similarly, all the blocks, there will be one inverter room. Okay, so here this is an inverter room for this one. This is an inverter room. This location is the substation, and here where it is. Yeah, here it is. This is the inverter room. Okay, so now how to think in a design perspective. Okay, so let's consider a solar PV plant rating of 50 megawatt. So 50, in simple words, we have to design the solar PV system for 50 megawatt at the grid interconnection point, or a POC, point of connection, or a POI, point of interconnection, or PCC, point of common coupling. In those point, we have to maintain 50 megawatt power. Okay, so for that, what we have to do? So we know how much is the power we have to maintain at the interconnection point, that is 50 megawatt. So next thing what we have to do, we have to uh, divide the 50 megawatt into number of inverter blocks. So here it is, total plant capacity is 50 megawatt, and considering this layout, so based on this layout, we can able to accommodate 4 inverter rooms, right? So individual inverter block equal to 50 by 4. So this will be 12.5 megawatt will come. Okay, so it means this particular one line, it's equal to 12.5 megawatt. Okay, similarly this also 12.5, third also 12.5, and fourth also 12.5. So individual inverter block, the maximum capacity is 12.5 megawatt. So this is the first step we have to do. Then second one, how the what is the rating of the inverter we are going to use? So I shown right in the last presentation. So this is the one inverter room or inverter block. So here we are having 5 winding inverter duty transformer. So 5 winding inverter duty transformer, one primary winding, 4 secondary winding. So in the 4 winding, there will be one inverter. Okay, so each inverter is rated for 3.125 megawatt. Okay, so 3.125 multiplied by 4, because we have 4 windings on 4 inverters. So it is rated for 12.5. Okay, so it is similar to like that. So first we have to arrive this inverter room configuration. How many inverters we are going to keep in a inverter room? Okay, so inverter block rating. The second step is inverter block rating. So that is equal to 12.5 megawatt. Okay. Hmm. So this is the second step. So for arriving this 12.5 megawatt inverter block, we have to do some background analysis in terms of technical and economical perspective. That is called the techno-economical aspects. So in that, what is the best suitable value is coming? So both meeting the technical requirements as well as the economical constraint. So we have to freeze. So first one is arriving the individual inverter block capacity, and second one is the inverter block rating. So we know, so each inverter block is rated for 12.5 megawatt. So how we are going to achieve? Okay, so we can achieve by using four number of 3.125 inverter, four number of 3.125, we can get 12.5. This is one option, or we can have the other option also. So that is two number of two number of 3.125 and another two number of 3.125. So okay, so this will be 6.25 and this will be 6.25. So in place of having a single transformer with four LV windings, we can go with two transformers. So here 3.125 will come. This loss also 3.125 will come. Okay. So the total this transformer rating is 6.25. Okay. So suppose having the similar set, then this also will be 3.25. So in a single location, we can get 12.5 if we are paralleling these two. Then this will be a 12.5. We can do like this also. This is an option one, and this will be option two. Option two. Okay, so for arriving this configuration, whether we are going to be going with option one or option two, so for that we have to do some technical commercial analysis. So which one is suitable for the particular location? There is no standard thing. We have to always follow four number of 3.125 megawatt to meet the requirement. It's not like that. So that depends on the location. Okay. So second one is the individual inverter rating. Then third one is energy requirement. Okay. So we energy requirement, energy requirement. Okay. So or we can say AC versus DC ratio. If you remember in the previous session, I told 1:1 ratio or 1:1.56 or 1 versus 1.4. So in the AC side, it is one only. So it means 12.5 megawatt block means this will be 12.5 only. But in the DC side, if it is 1:1 means it is 12.5 only. But if it is 1.56 means we have to consider 12.5 multiplied by 1.56. So how much value is coming? That is the value we have to consider here. So it means for maintaining this 1 is to 1.56 DC ratio, so we have to install 12.5 multiplied by 1.56. So how much value is coming? That much power capacity solar PV panel we have to install. Okay, so why we have to go for 1.1 versus 1.56? The reason is that we have to maintain two things. The first one is the power, that is for 50 megawatt plant we have to maintain 50 megawatt power, that is the first one. Then second one is energy, energy kilowatt hour we have to maintain. Okay, so 50 megawatt plant operating for 1 year duration, how much amount of energy this plant minimum has to produce? Okay, let's say some 3000, sorry, 3 lakh, let's consider 3500 megawatt hour it has to produce. This is a typical value. Okay, so we have to satisfy two conditions. One is power. So power, how we are considering 12.5 multiplied by 4. So we have 4 inverter rooms. That is this 4, 12.5 inverter block capacity 12.5. So multiplying 12.5 with 4, we will get 50 megawatt. So we can able to meet the power requirement. And the same time we have to meet the energy requirement for the particular year. So that is, in this example it is 3500 megawatt hour. So in order to meet this 3500 megawatt hour, so we have to increase the DC capacity. Why? I already told the solar will operate like this. If we plot the power versus time characteristics, y-axis it is power, x-axis it is time. Okay, so solar will start morning 6 o'clock and it will end at evening 6 o'clock. So the maximum power will start 10 o'clock in the morning to 3 o'clock in the evening. Okay, so in this area only it will solar will generate maximum power. This area and all we are having the lesser amount of power. Okay, so here it is 4 hours, 6 to 10 it is 4 hour, again 3 to 6 it is 3 hours. Okay, totally 7 hours in a day. So totally daytime is 12 hours. In 12, among the 12 hours, 7 hours in a particular day, we are having the lesser power generation. Okay, so during that time, the solar plant will not produce 50 megawatt. That time it will produce very less amount based on the availability of irradiance. So it will produce the lesser power. Okay, if the power is less means absolutely energy produced during these hours. Okay, energy produced during these hours also will become less. Okay, so due to that we are not able to meet this 3500 megawatt hour of energy. Okay, so for that what we will do, we will increase the DC capacity. So in place of 1 versus 1 AC DC ratio, we are going to have 1.56 in place of 1. So it means we are increasing the DC capacity to a higher value. So that time the power curve it will not be like this. Okay, so that time it will go like this, will go like this. So it will not be like this, so it will go like this. So by increasing the DC panel capacity, we can able to get more amount of energy in a lesser time duration as well. So that is the purpose of having the higher AC versus DC ratio. Okay, so this is the third step. Okay, so this is the three major steps involved in designing of any ground mounted solar PV system. So this is the very broader way. So in a micro level, for designing of the PV system, we have to go with we have to do the calculation for AC cable sizing. How much size of AC cable we are going to use from the inverter to the inverter duty transformer, from inverter duty transformer. So in this diagram for the AC cable, here AC cable will come, here AC cable will come, this will be an AC cable. Okay, this sizing we have to do. Then second one is the DC. Okay, this is an inverter, this is the PV panel. So for an example, this is the PV panel, positive, negative will be there. So here will be, this will be an inverter. Okay, so we have to connect, right? We have to connect the positive and negative terminal of the panel to the inverter positive terminal. So this cable length, we have to do the sizing and calculation. Okay, so that thing also we have to do AC cable sizing, DC cable sizing, then this inverter sizing also we have to do. So these are all some micro level steps. Okay, and another important thing, some of the requirement demands for losses in a system. Okay, for considering a 50 megawatt plant or 100 megawatt plant, the plant is more than 100 megawatt and all, the amount of cable required in the plant will very high. Okay, for an 200 megawatt plant, at least we need 3 lakh to 4 lakh kilometers of cable. Sorry, 3 lakh meters of cable, 3 lakh to 5 lakh meters of cable. Okay, so that cable is required for DC cable, DC cabling and AC cabling. So minimum 3 lakh to 5 lakh meters of cable is required. Okay, so whenever the power flowing through the cable, there will be a loss in the cable. So there will be a loss in the DC cable, there will be a loss in the AC cable, and there will be a loss in the transformer as well. Okay, so as I told here, we have to maintain the energy of 3500 megawatt hour at the interconnection point minimum. Okay, so by considering the losses, so what are the losses in the plant we have? So one is the DC loss, then AC loss. Okay, so in the DC loss, what are the losses will come? DC cable. Okay, and inverter also there will be some losses. Okay, in the AC cable, what are in the AC seat, what are the losses will come? Inverter due to transformer, the transformer what I shown, in the transformer also the losses will be there, and the AC cables, the AC cables, what go are using to connecting the inverter to the inverter duty transformer, cable used in this collector network. These are all the cables. We can expect the losses. We can expect more amount of losses. So we have to consider that also. Okay. So for maintaining 3500 megawatt hour. Okay, so energy requirement equal to minimum we need how much we need 3500 megawatt hour. In order to get 3500 megawatt hour at the interconnection point, we have to consider the plant losses as well. Okay, we have to maintain the DC loss as well as the AC loss. So in the DC losses, DC cable and inverter will come, and AC side, inverter duty transformer, then AC cable. Then if there is a transformer at the substation, and the transmission line from the uh, substation to the interconnection point, those also will encounter the loss. So those also we have to include. Okay, so now the energy requirement is no longer 3500 megawatt hour. By considering the DC and AC losses, the energy requirement may be increased to 3600 or 700 megawatt hour. Okay, this is the total energy requirement considering the losses. Okay, so here what I told, right, 1 versus 1.56. So this 1 versus 1.56 we have to taken care considering the losses in the system. So it including the DC cable loss, inverter loss, then AC cable loss, inverter duty transformer loss, then power transformer in the substation loss, then a transmission line between the substation to the interconnection point. Okay, so like this we have to consider the AC versus DC ratio. So for doing these energy requirement analysis, there is a software called PV Syst, PV Syst, PV Sol, like that. There are various softwares are there. So PV Syst is the one of the widely used software in the renewable power plants like solar PV power plants for analyzing the energy requirements. So by considering the plant capacity, inverter configuration, solar PV panel, what is the rating we are going to use, then losses in the PV plant, then considering some other factors. So how much amount of energy we are going to get. So those things we can able to do it in this PV system. Okay, so with this software we can able to do some analysis. So after that, so that will be helpful for arriving this AC versus DC ratio. Okay, so some projects the tender specification specify the maximum power loss in the DC cable shall not exceed 1% of the total loss. In the AC side, 0.6 percentage of the total loss, it is the maximum. So for the DC loss, 1% is the maximum. AC loss, 0.6 percentage is maximum for the cable, inverter duty transformer, like that. Some projects demands this one. So for that, we have to again do some calculations. So how much amount of losses we can expect in the system. So it is the real power loss. So we can calculate by means of I square R. So here R is the total resistance. R is the resistance and I is the current flowing through the cables. Okay. So if we are having some this is the panel one inverter. Okay, so like this n numbers will be there. This will be cable connection one, this will be n. So for that what we have to do, we have to calculate I square r for this and I square r for all the cable up to n. Okay, then what we have to do, we have to add this one to n. So how much amount here some value will be there, right? So that is the total DC loss. Similarly for the AC loss, so this loss we are having the DC loss divided by, if we put the total losses of the plant, then we can able to know how much is the DC loss in percentage. That percentage we have to maintain at less than 1. Okay, so we have to maintain less than 1. If it is exceeding 1 percentage, so in that case we have to do some alterations in the layout. In this layout we have to do some alterations, moving the inverter room to the center, or reducing the DC cable length, or increasing the size of the DC cable length. So in that we are like that, we have to do some optimizations, and we have to reduce the losses for the AC cable as well as the DC cable. Okay, so everyone is clear as of now. Anyone have any doubt in this? If there is no doubt, I will continue further. Okay, so total energy, we have to consider the AC losses as well as the DC losses also. Okay, so and some other factors what we need to consider is that the location of the interconnection. Okay, so you consider here our solar plant is there. Suppose we are going to connect the solar plant to the existing substation. Existing substation. Suppose if this plant in our Tamil Nadu, so TNEB is the grid electricity board. So they are having already, there will be some substation. Okay, so at what location we have to meet this requirement? 50 megawatt, 3500 megawatt hour, at what location we have to meet? Okay, for an example, suppose this is an point POI, point of interconnection, whether we have to connect this is a plant, PV plant. So after this line, this will be an plant. This side will be up to this level. This will be a transmission line from the PV plant to the interconnection substation. This portion will be the substation, TNEB substation. Whether we are going to comply this 50 megawatt, 3500 megawatt hour at this location, at a plant level location, or at the interconnection substation location. Okay, so here the difference is that if we are considering at this location, we no need to consider the losses in the transmission line. Okay, so in the AC losses, the transmission line losses will be excluded if we are considering the compliance point at the plant level. Suppose we need to consider at the interconnection location at this area, we have to comply. This point is called as uh, point of interconnection POI. This point will be point of connection POC. So point of connection POC is this point. Point of interconnection POI is this point. So if we need to consider this point, then we have to include the losses in the transmission line as well. Losses in transmission line also we have to consider in the AC loss. Okay, so this factor also we have to consider uh, for designing any ground mounted solar PV plant. Suppose if these informations are not available clearly, then we have to ask for it. So at what point we have to comply the power as well as the energy requirement. Okay, so I hope everyone is clear as of now. So up to this point, I told the losses in the PV plant cable and um, transformers and collector networks. Okay. So due to that, what will happen? For an example, this is the PV plant, right? In the single line diagram. So let's consider these inverters. All the inverters are rated for 50 megawatt. Okay. So this is the interconnection point. Here we have to maintain 50. Here we have to maintain 50. So this is the collector network. Here the cables will be there. Let's say it is 33 kV cable. So this 33 kV cable, let's assume the cable length is almost 100 kilometers. So totally we are going to have 100 kilometer length of cable. Okay. So the inverters are rated for 50 megawatt. So due to the losses in the AC cable at this location, then inverter duty transformer and the AC cable, the at the interconnection point we can't get 50 megawatt, so it will be reduced to some other value. It will not be 50 megawatt. So here we are having the total inverter capacity is 50 megawatt, right? So at power at interconnection point Pi equal to 50 minus P losses in the AC cable at this location, cable losses in this location, then inverter duty transformer P IDT loss, then P collector network loss. P collector network class we have to consider. P collector network class consider. So the at the interconnection point power will not be 50 megawatt. The power may be reduced to some 46 megawatt. This is some approximate value. Power at interconnection point is 46 megawatt only we can able to get it. So this is no longer 50 megawatt, this will become 46 megawatt. Okay. So so in this condition, this we are not able to maintain at the interconnection point. We have to maintain 50 megawatt power requirement and 3500 megawatt energy requirement. So due to the losses in the plant equipments, we are not able to meet at the 50 megawatt at the interconnection point. Okay. So in order to bring this 50 megawatt 46 megawatt to 50 megawatt at interconnection location, what we have to do, we have to add one more uh, PV inverter, or we have to add some DC capacity. Okay, so that including some here, how much is the how much value is reduced to 4 megawatt. Okay, so we have to install the solar inverter and its DC panel capacity shall be more than 4 megawatt. Okay, because there will be some losses associated at this point. Okay, so we have to install one more block which power rating is equal to 4 megawatt, little bit higher, right? So these are all some of the design aspects we have to consider for designing of any solar PV system. Okay. So now I will take you the software normally which will useful for the grid compliance analysis. This is the software called Dick Silent Power Factory. So in this software, I will just explain what are the things. Okay. So this is the power grid like our TNEB. TNEB. This is the power grid. Okay. So this is at 33 kV voltage level. So here there will be no substation actually. So the power we are considering, we are exporting the power at the medium voltage 33 kV itself. So our grid interconnection voltage is 33 kV. Okay, so this will be a grid and this will be our plant up to this portion, up to this portion, except grid will be our plant location. Except this grid, the remaining equipments will be our plant location. This grid will be at the substation of the TNEB. Okay, so this bus is the main medium voltage bus. So from this bus, the collector network I told you, right? So collector network means this is the cable, 5 kilometer length. So this cable, what we will do, we'll told, right, one inverter room. So this will be one inverter room. So it including the transformer. This is the 5 winding transformer, one primary winding, four number of LV winding. So primary winding is 33 kV and four number of LV winding is 690 volt. Okay. So its power rating is 3.125 MVA. So totally 12.5 MVA capacity transformer, this one. Okay, so it will be connected to the PV panel. So this is the PV panel in Dixisland Power Factory. So it's equally rated to 3.125 MVA. Okay, 3.125 MVA. We have rated this inverter. Okay, so similarly, up to this one will be one inverter block. This will be a second inverter block. This will be a third inverter block. This will be a four inverter block. Okay, so now we are having the plant capacity which is equivalent to 50 megawatt. Okay, now I am just running the load flow analysis. Maybe the electrical engineer who studied the power system analysis may know what is load flow analysis. So now I am executing the load flow analysis. You can able to see. So at this moment, each inverter is delivering 3.125 megawatt of active power. 3.1 megawatt of active power. Okay. So here, the one inverter block is connected to another inverter block, and this block is connected to the main MB bus. Okay, it's like a radial type of connection. Okay, so the total plant capacity is 50 megawatt inverter capacity. So, and at the interconnection level, we are getting almost, you can able to see 46.7 megawatt only we are getting at the interconnection point. Okay, so remaining 3.3 megawatt, what happened to that? That is the losses in the system. So losses in this cable, medium voltage cable, that is a collector network cable, losses in this collector network cable, then losses in this inverter duty transformer, then losses in this DC cables. Okay, so these are all the things we have to consider. So now it is no longer 46.7 megawatt. Sorry, 50 megawatt. It is presently it is 46.7 megawatt only. Okay, if we add one more block like this, or we have to add minimum another 4 megawatt into it, then it will become 50 megawatt. So we have to maintain the minimum requirement of 50 megawatt. So for that we have to add one more inverter inverter not inverter block. We have to add one more inverter in this plant, so that we can able to get this. Okay, so this is the Dixieland Power Factory software. This software is used for only for the electrical power related aspects, not for the energy related aspects. Energy related aspects we have to use the PV Syst software. For the power related things, we can use this Dixieland Power Factory software. Okay. Okay, so I think we came to this end of this presentation. I will summarize in this presentation. I covered the design aspects of a 50 megawatt solar PV plant by considering inverter, by considering the layout based on the land availability, the useful land availability. um, we have to design the solar PV plan. So the first step, we have to arrive the inverter block capacity. Then that is the first step. So in this example, we have seen 50 divided by 4, that is 4 inverter blocks. So 12.5 megawatt is the individual inverter block capacity. So the next step is how we are going to get 12.5 megawatt inverter block capacity. How we are going to get? So I explained the two option. 4 number of 3.125 MVA inverter connected to one 5 winding transformer. It has one HV winding and 4 LV windings. That is the one option. Or the second option, two number of 3.25 MVA transformer with 2 LV windings. So by combining 6.25 MVA two numbers, we can get 12.5 megawatt. So for doing that, we have to do some techno commercial analysis. So based on that, we have to arrive that value. Then third one is the AC versus DC ratio. So I given one example for one versus one AC versus DC ratio. Then second one is 1:1.56 AC versus DC ratio. So that is the typical value. So how I also told how to calculate that value. So for that we have to consider how much is the energy requirement. So in addition to that, we have to add losses in the DC network, it including the DC cables, inverters, and the AC network, it including the AC cables between the inverter duty transformers, then inverter duty transformers, then medium voltage cable network. Suppose if any substation is there in the plant, we have to consider the losses in the power transformer, then losses in the transmission line, and also where the location we have to meet the complaints, the transmission line between the solar plant to the existing TNEB grid substation, whether we have to consider or not. So I given that example as well. And also I opened this Dixieland Power Factory software, and I shown the typical single line diagram of 50 megawatt plant with 4 inverter blocks, and also I explained the losses in the PV system. Okay, so if you want to see the losses in the cable, it will tell you. losses total. So how much is the losses happened in all the cables we can able to see. Okay, so for this particular cable, 50.1 kilowatt is the losses. In the next this cable, 100.3 kilowatt is the loss, and this cable 6.3 is the loss, and the next cable 25.1 kilowatt is the loss, and this cable 6.3 kilowatt is the losses happened. So if we combine, so almost 150 160 163 kilowatt is the losses happening in this collector network cable. Okay, so that's all for today presentation. So in the next presentation I will touch upon the solar PV for the ship fisheries, as well as the business model for the solar PV system. Okay, so most probably the next session will be the last session for this interaction program. Then after that, I will engage one more session for a dedicated one Q&A session. So I will not present anything to you. So I will clarify if you what are the doubts you have for the solar PV system. I will try to clarify you in that session. Okay. So now if you have any questions, you please ask.